Right. Good morning, good afternoon, good evening, everyone. Wherever you are, welcome to Uptime 2020 Virtual Conference sponsored by Runecast. My name is Sunny Dua, and I'm a Senior Product Line Manager with VMware. Today, I'm going to talk about how we can leverage artificial intelligence to derive full stack root cause analysis. It's 7 a.m. over here in California, and I'm enjoying my coffee. I thought I'll welcome you with my Twitter handle so that in case you want to ask questions offline, then you can always reach out on Twitter, which is @sunny_dua. And my website and the blog is sunnydua.com. I'm a product manager with a passion to solve problems. I've been working in the industry for the past 17 years across the stack. And luckily, I've started my journey with servers and now doing management software. So essentially, I've worked with full stack. So I'll talk about how, when problems happen in a full stack environment, you can leverage tools from VMware which can help you do a root cause analysis. Before I get started, I would quickly show you a slide, which is the disclaimer slide. Essentially, what I'm showing over here, everything is a feature and a product which is available out today. But as a product manager, sometimes I talk about future. So in case I do, don't hold me to that. Okay, so let me just move on and kind of talk about a few housekeeping items. First of all, you can use the Q&A panel on Hubilo in case you want to, or you can use the chat window over here in Zoom to ask questions. I will take the questions as I go and answer them at the end of the session or as they come in. So we'll look out for those. I'm driving solo today, so I will take on the questions as and when I take a break. A copy of the deck would be shared later. No need to take screenshots. And most importantly, have fun. Let's just go through some good content and some demos, and we'll see, and we'll make sure this is useful for you. And have fun on the way as well. Okay, so let's just go to the next one. Okay, so I wanted to start with this slide because the industry itself is kind of transforming. Like every other industry, the management industry and the operations industry is also transforming. We are seeing our customers moving from the need of being monitoring something and reacting to issues which are happening in the environment, and then going ahead and making changes to solve those problems. Now, those days are slowly going away because customers are more and more asking for being proactive, right? And the reason for being proactive is because they want to make sure that their services, whatever they're providing from their IT infrastructure, are highly available, and they want to increase the availability. So monitoring is one space. The second space is around remediation, where customers want to recover services as soon as an incident happens. Now, of course, you can be proactive the whole day, but there would be cases where incidents would happen and problems will occur in your environment. In such scenarios, you want to make sure that you can recover the services as soon as possible. The third one is observability. Now, essentially, you would notice that a lot of companies are calling their tools as observability tool and people moving towards observability. But essentially, uh, this is a method of looking at the unknown unknown, which means that you are not sure what the issue is, you're not sure what's brewing up and what's the root cause is, and you're trying to take data-driven approach where you're looking at a lot of data together in a meaningful way so that you can gauge information out of it and then take decisions which will allow you to find the root cause of an unknown unknown brewing in your environment. And again, you want to do that because you want to make sure that next time such a situation happens, you're able to capture it and recover automatically out of it, and hence increase the reliability of your service. Now, imagine if your internet connection is bad, right? And sometimes it kind of drops and then it comes back again, and then things work fine. The problem is that while you have recovered and your internet is working fine at the moment, the service is no longer reliable because you don't know the root cause. So unless you start tracking the wire, the cable modem, the wire back from your home to the junction box in your area, to back to the services company provider, you will not be able to find the root cause. So it's important that you take all those data points to come up at a data with a data-driven decision and find out what the root cause is. That's all about observability and increasing the service reliability. All right, so let's talk about AI a little bit and other concepts in terms of how we can leverage artificial intelligence by taking in a big set of data and performing this analytics on top of it so that you can come to a root cause analysis in a fully automated way as much as possible. Okay, so before jumping in, let's just look at some of the concepts. So I know people use AI, ML, big data analytics all interchangeably. And it's kind of okay because people do, everything is born from a single source, right? Now, however, there is differences, a lot of differences in terms of how each of these functions or how each of these technologies work. Now, if we talk about machine learning, at the heart of machine learning is, again, a statistical technique. It's mathematics, but it's essential that this mathematics runs based on what the developer has coded. And then the code itself transforms over a period of time by learning new behavior from a given environment or given set of data. That's machine learning. Again, you're continuously learning, changing the course of action, and going ahead and getting to new results, and then learning from those results again, and going ahead and changing again. Now, if you are into multiple such layers of learning, then some people call it neural networks. And neural networks are applied where you want to do deep learning. Now, our brain is set of is a great example for neural networks, right? And you can do deep learning as human beings. It's nowhere close to what human beings can do um, in terms of what machines can do. Now, again, all of this happens because you have a lot of a way to ingest a lot of data, capture the data, and do analysis on top of this data. And that's what is termed as big data or data lake. And ultimately, when you're doing analytics on top of it, that's where you do some kind of discovery, interpretation, and communication of meaningful patterns in the data. So now you're starting to write algorithms which can scrub through the data and come up with some kind of patterns using which you can go ahead and start learning and then reinforcing certain behavior. Now, to the tip of it is artificial intelligence, right? Where you understand certain behaviors and then you want the machine to mimic those cognitive functions so that it can go ahead and learn and then resolve problems as well. And that's where problem solving comes into picture with artificial intelligence. So today, as I move forward, I'll talk about how we leverage some of the nuggets or some of the algorithms which help us go ahead and learn from huge data sets in a cloud environment, and then run analytics on top of it and come up with certain evidences which can help you find root cause to problems which might be across a given stack, starting from applications down to the disk in the infrastructure. All right. So let's just kind of look at what product set I'm talking about, and these are a couple of slides which will talk about what exactly we are trying to do or what I just described. So whether you're running on a VMware cloud environment or whether you're running on an edge in an edge or data center, whether you're running in a VMware cloud provider program or partner, or you're running in VMware Cloud on AWS, or if you're running in native public cloud, from all these environments the goal is to be able to discover, collect, and persist data, to be able to go ahead and do dependency mapping, to be able to create a topology, and then capture metrics, events, configuration, logs, and flows, all of these resources, and feed that into the AI engine of vRealize operations. Now, once this AI engine is crunching through a lot of data, the algorithms at the end of the day help you perform or get to certain use cases. I mean, as a customer or as a user, you don't care about what the algorithm is. What you care about is the outcome, and those are these use cases for the administrator who's trying to monitor or manage an environment. Now, as talking about an administrator, there are different personas. There could be a virtual infrastructure administrator, there could be a network administrator, or a cloud administrator. Each of them can come to an engine like this and go ahead and define what their intent is. Their intent could be operational. which is they want to make sure that they have the best performance, highest utilization, efficient capacity, and so on and so forth. That's all operations. And the second piece is business intent. In case of business intent, you want to make sure that and this minimum cost spent to run an application, it's in compliance and it's meeting a service level A or B because you promised that back to the business. So again, those are intents and policies which are ingested into the system by the humans, and then those are considered by the AI engine while going ahead and giving you the outcomes on those specific use cases. And speaking of the outcomes, again, these are numbers which are coming out of different analyst studies talking about how this engine has helped our customers reduce the unplanned downtime, which we spoke about earlier, reduce the mean time to resolution, and again, doing a lot of efficiency around hardware as well. So I'm not going through all those details, but you see that that's the kind of the proof of the pudding. So let's see how you can consume this software, right? So vRealize Operation Suite comes exactly in two form factors. The first one is the on-premises version, which has been out there for close to a decade, and the same software base is being leveraged now to go ahead and produce the vRealize Operations cloud service. So again, as a user or as a consumer of the software, depending upon what your cloud strategy is, whether it's a private cloud with a little bit investment in public cloud, or whether it's migrating fully to public cloud, or whether you were born in the public cloud and you have some private cloud as well. In any of these cases, you're able to leverage vRealize Operations or vRealize Operations Cloud and ensure that you're getting the same set of scalability, security, resilience, and an API-driven environment so that you can leverage it as you go in and run operations. Now, how do we do this? So let's just kind of talk about discovery. So I'll quickly run through some of these slides, but the idea here is that we are able to discover data from physical infrastructure, and there are hundreds of physical infrastructure plugins which are available to get data into the platform, because that's the key. The second is around SDDC and virtualization layer. So while it's a VMware product, it's agnostic to different hypervisors, going up to even IBM Power hypervisor. And then on top of that, the IaaS platforms. So whether it's Kubernetes or whether it's Pivotal Cloud Foundry or VMware Cloud on AWS or other IaaS providers or cloud providers such as AWS, Azure, Google, and so on and so forth. All the data can be ingested from the IaaS platforms. And finally, the package services or packaged applications, which can also suck in data and get you this data inside the platform. Now, when you talk about data, what we discover and collect is a realm of data starting from metrics, events, configs, logs, relations, and with vRealize Network Insight, we also get the flow data, which talks about the communication between um, two entities over the network by just leveraging network flow information in order to tell you whether communication is happening or not. And ultimately, all this data is used to classify. And this is one big important step when it comes to artificial intelligence, that you're able to classify and label your data set in a way that it can be leveraged later on to run algorithms on the right set of data set. Now, some systems do auto labeling and some systems use manual labeling. With vRealize operations, we leverage the concept of resource kinds, which can automatically label certain object types based on manage object IDs coming from the source. And then the user is able to define relationships on those object types as well in order to build a full stack topology. And these relationships are, I would say, the key and the core of the product as well. Okay, just getting my coffee there. Okay, so one part is around getting data. The second part is around getting data at higher ingestion rates. And this is purely critical when you talk about cloud native applications, or when you talk about high performance compute or applications which are latency sensitive. Now, in all these cases, you want to collect at the speed of light if possible, although that comes with its cost. But with vRealize operations in the cloud, the specific capability which you get, in addition to what you get um, um, in addition to all the base capability which you get with vRealize operations, is this real-time monitoring capability, which means that you can ingest data near real time to begin with the vCenter environments, and then get eventing, alerting, trending, forecasting, everything on the near real-time basis. And this data is kind of kept for at least 3 days for somebody to come back and do the analysis if they have to. Okay, so now we've finished the ingestion part. Let me just talk quickly about, not quickly, but I'll take some time here. And this is where we'll talk about how exactly we take this data and then we run this through the AI engine and use different algorithms within the AI space in order to achieve the use cases. So let's just kind of look at this, and I'll break it down so that we can go one by one before we deep dive into each of these areas. So I call it the components of the self-driving operations engine. So essentially, to simplify, these are the analytics or the algorithms which are AI driven, which go ahead and help solve certain use cases. And in the back end, I'll give you some introduction to what are the technologies which are used as we go through. So the first one, and this goes back to our three themes which we talked about earlier, right? The first one is being predictive and being proactive. Now, in order to be predictive and proactive, what you need to know is the future. Because if you don't know the future, you will not be able to go ahead and make changes to the current or to the to today in order to make sure that your future is happy. So if you know that the future is bad, then you are able to make those corrections today. And that's where predictive forecasting comes into picture. Now, um, this technology is essentially a real-time ingestion technology into a capacity engine or a forecasting engine within vRealize operations. What it does is it takes any data point right at ingestion, which means as data is being sent into the or collected by the product, it runs through this algorithm, a set of algorithms, in order to go ahead and prime a forecast. And this is done for every critical KPI in the system, which can define performance as a behavior or capacity as a behavior for a given entity. Let's take an example of virtual machine. Now, this is where the data coming in and going out might sound very simple because yes, I'm getting a data point in and I'm forecasting into the future how how much smart that is because every second algorithm can do that. Now, the use cases which we're working on are very critical, and hence we had to model this algorithm or this particular forecasting engine by using some of the open source principles available through ARMA, which is auto-regressive moving averages. Again, it's statistics, but how do you take statistics and apply AI on top of it? So the AI pieces which are available are things like periodicity, and I'll talk about that in the next slide. So I'll not spend a lot of time, but we'll kind of go through that. Calendar awareness, then discrete and fast Fourier transformation, and real-time forecasting, and deciding what exactly would be the trend of the forecast. Things like exponential decay, which means you can give more weightage to recent data without losing periodicity. And when I say periodicity, it's all about learning periodic behaviors so that you understand whether a particular spike in the system is a real data point or it's something which the system should ignore because it's an anomaly, right? So that's where predictive forecasting comes into picture. The use cases you solve with this is things like predictive DRS. You want to make sure that DRS is placing a VM even before the host goes hot or the VM on the host faces contention. The second is right sizing. So again, if you know the future and what will be the utilization of a workload in the future, then you can right size the workload today and make sure that it will not run out of capacity in the upcoming future as well. Um, Workload placement and balance, and I'll give you some examples of that. But it essentially means that how can you place VMs or workloads so that they get optimal performance from day zero itself. And balancing means that on day two, if there are changes in the environment, then you're able to move the workloads from one environment to another for them to achieve what they need in terms of performance. And finally, the fourth use case is capacity analytics, which is long-term capacity planning, which allows you to make the right set of decisions today so that in future, you're not scrambling for capacity when you are facing performance issues or applications are struggling and line of business is unhappy. Again, predictive forecasting is all about being proactive. And if you're doing things right in the first place, then you should not have performance or capacity issues in the future. And that's the goal over here with these algorithms. And I'll go into the details of what each of these and how they work. The second one is around root cause and anomaly detection. So while the topic says how can you do root cause analysis, I would want to stay away with it till the time I can proactively solve problems. And that's where predictive forecasting comes into picture. Now, with root cause and anomaly detection, we are talking about after the fact in most cases, right? Things have happened or are about to happen because you're too close to that problem. And now you might not be able to stop it, but you might be able to catch it and go ahead and start the process of remediation and recover, as I said earlier, service recoverability. And then from recoverability, you can move into reliability because you can find the root cause. So these are the kind of, this covers the second and the third pillar from service recoverability to service reliability. How do you do that? The first thing is known problems. If you have known problems, you'll get an alert and you go ahead and start troubleshooting. Now, alerting, troubleshooting, doing correlation, finding root cause are all part of this root cause and anomaly detection engine, which has several different AI algorithms which come into picture and start giving you outcomes. So again, I'll talk about some of these as we move forward, but the relationship is one, to be able to build a dynamic relationship, to be able to build or find dynamically changing metrics and anomalous metrics, to be able to correlate metrics from with each other in a full stack, and then to be able to rank or prioritize alerts and issues which are happening in the environment using telemetry based analytics or using rarity analysis. And I'll kind of go through that as well as we move forward. Okay, the last part is the action framework. So I think we talked about it earlier, that if you want recoverability in a system, you want to make sure that the AI is able to take an action and can bring back the outcomes of that and feed that into the loop again. And that's where the action framework comes into picture, where you can do self-healing based on orchestrator or approval workflows or configure remediation to ensure that you are able to continuously maintain the hygiene in the system which you want for your system to perform well. Okay, so with these three in mind, let's see the application of each of them into the product and into the use cases so that we can see how effective they could be. And I'll try to kind of go through some of this content pretty quickly, but yeah, keep getting your questions coming in on the chat or on the Q&A panel as you want to go in. Okay, so let's start with proactive operations. Again, as I said, this is the analytics, which is driving the four use cases. I think I talked about it earlier, but essentially, there are multiple different sub-analytics which is built into this graph itself. So let's focus on this graph for a second. What you see on the left-hand side is the data points coming in, and these are coming in every 5 minutes. So the algorithm is taking the data and continuously shifting into the future in terms of forecasting. If you look at the line in the center, which is now, everything behind that is data points which have come in the last 5 minutes and before. Now, when I say before, the great news is that this algorithm can prime any set of historical data because it's real time. You're not really looking behind, but you're looking forward, which means that you're getting the data every time it is collected and it's fetched into the system, and that is now embedded into the system. So no longer you have to worry about running a bad job to see what exactly happened in the past. And then from this point onwards, everything is forecasted into the future. And like with any forecasting engine or algorithm, you would always have a certain amount of confidence in your forecast. The more historical data you have seen or historical patterns you have learned, the better your forecast projection would be and the confidence level would be. And that's where the confidence bands comes into the picture, the gray band hugging the dotted blue line there. And then you can see that the future prediction is based on the recent historical data itself. What I mean there is that if you look at the left-hand side, you will see all historical data and the recent data. Now, this is where the algorithm becomes smarter as it learns the environment, because you want to make sure that you're able to react to recent changes and forecast based on that and not rely on everything in the past. And then there are things like calendar awareness and self-learning, which is available within this particular algorithm and the use cases I talked about earlier. So let's look at the application of how exactly this algorithm manifests itself in larger environments where there might be different data patterns coming from different workloads. Just getting my coffee. Okay, so essentially you could have peaks which can be of different nature in a given environment. It could be momentary, sustained, or periodic. Now, in this particular case, what we are talking about is the momentary peaks, sustained peaks, and periodic peaks and how they're captured by the system. Now, given that you might be having peaks of every different nature, the system automatically understands if the peaks are short-lived or sustained. Um, all right, I might have, let me just make sure that I have the right view for you guys. Okay, all right, perfect. So again, you might have momentary peaks, sustained peaks, or periodic peaks. In any of these behaviors are learned by the algorithm. Point driving the point to the fact, right? If there is a single peak which has happened in the environment, it has never occurred in the past, then the system should be able to ignore it automatically. If it's a sustained peak, which means it is not periodic but has ran for a longer period of time, the projection will take that into account. However, it will automatically lessen over a period of time because of something called exponential decay, which I'll discuss in a second. And then periodic peaks, which means that I'm able to understand cyclical patterns and waves, whether they're daily, hourly, daily, weekly, monthly, last day of the month, etc. So there where you can understand workloads which happen, let's say as a bad job, which is running in applications at the end of the month. And the system understands and also detects those particular patterns. Okay, so let's look at the projection models then, right? So as data comes in, you're able to learn what the linearity is in the projection as well, and then project that into the system, right? So the system identifies whether a particular trend is steadily increasing or whether it's a huge jump which has happened. For instance, the projection needs to understand, and this one does, if you're running a backup job, which will start at 9 p.m. and it'll shoot at 95% and then run sustained workload at 95 or even 100% for the next 4 hours. Now, if the system sees those step functions in the linearity model, it automatically smoothens it out into a projection because it understands that these step functions does not mean that the system will start using 500% CPU or 1000% memory because it has certainly jumped. So understanding how linear regression needs to be done is a part of this algorithm as well. Again, some key examples, but something which will help you understand how exactly data has to be analyzed. Now, this is all human intelligence, if you look at it, which is artificially built into the system for the system to learn and react to different data points. The other thing is periodic models. Again, I spoke about some of this earlier, but to be able to understand hours, days, weeks, months, having calendar awareness, understand square waves, which are happening in the environment, such as backup jobs, um, handling any kind of noise which might happen in the environment. And these periodic models, you can Google them as well, are all based on ARIMA, which is open source, and leveraging FFTs, uh, pulse model, and edge detection and wavelets are some of these capabilities which are built into the algorithm to prime this data as it comes through. All right. So Now, finally, the point which is important, and this kind of mentions the versions of vRealize operations as well. Now, earlier in VROps 6.6.1, if you're using that version, you do not have any of this AI stuff in that. So just kind of letting you know, that is more dependent on a sliding window, which looks at a fixed set of data in the history and runs an algorithm or a batch job every 24 hours to do capacity analytics and performance analytics. In case of vRealize operations, 6.7 and above, everything is open window, which means that we take all the data points into consideration. And as I said earlier, because it's ingestion of data as it's collected into the engine. And the last one is exponential decay. So with 7.0 and 7.5, we learn new behaviors which we have applied further on this model to make them more intelligent. And I spoke about it. It's called exponential decay. But what it means is, let me just switch to the next slide and talk about it. So what it means is that when you're looking at exponential decay, then the system is giving higher weight data points or data weightage or weightage to recent data as compared to older data. Now, each one of you who have been IT admins or administrator of a VMware environment might have experienced this. You go ahead and create virtual machines for your application team because they want it. So you go ahead and create them in January, for example. And then you would notice that for the next 6 months, nobody does anything on those, or they might have tested it for a couple of times. But 6 months later, suddenly all of them start shooting up your CPU and memory cycles because they all start using resources. Now, that's the reality of a workload on a data center today. They are spun up, especially in a private cloud, when people have time or when they think they will need the workload. And then at some point of time, application lands on that particular workload and starts leveraging the resources. Now, if I look at a pattern of, let's say, CPU usage of sort of such a virtual machine, I will see 5% usage sustained over a period of time for 5 months or 6 months, and suddenly it'll shoot up to 75% CPU usage. Now, that'll be the graph at the bottom if you think about it. You would want to make sure that you understand this changing behavior exponentially and decay the older behavior so that you're not giving higher weightage to that. And that's what is built in into the system. It understands recent changes and based on that reacts uh, to make sure that the forecast is primed based on that. Okay, so let's look at a couple of examples as to how all of this mumbo jumbo happening in the backend interfaces an end user, because that is what is most important, right? The AI is not important, the outcome is. So let me take about a couple of slides to kind of explain that. So imagine from a user perspective, you'll not be worried about whether exponential decay is working or what kind of data period data is being looked at. What you're worried about is outcome, and those outcomes will be based on your input. So imagine and those inputs can be done through business intent and operational intent, which I explained earlier. So imagine you have a VMware SDDC stack. You have two clusters in your data center, and both are vSAN cluster. And now you want to go ahead and apply a business and operational intent to them. So let's look at the state of the cluster first. So right now the clusters are running workloads, and there are a few Windows workloads, a few Linux workloads on cluster A and also on cluster B. But you can see that the dotted box is basically the full capacity of the cluster, right? The dotted line over there, the rectangle. You can see that one cluster is full on capacity. There is some fragmented capacity left over. And on the left-hand side, you can see that there are big boxes and big VMs running, some small VMs running, but again, there's a lot of fragmented capacity left over there as well. And this is a typical data center environment, which is not managed by a tooling or a system which can take decisions for a customer to make sure that everything is equally used, because it's humanly impossible for somebody to sit with an Excel sheet and decide which VM should be placed where and what should be the size of the VM so that everything is optimally used. And if things are not optimally used, you will have performance problems. So let's look at that. So essentially, you apply the business intent that I want the Windows machines to run on cluster on the left. I want the Linux machines to run on clusters on the right. And that's done through tags, vSphere tags. That's what the system enforces or asks or applies as an intent. Then you want an operational intent that none of my clusters should run hot. Hence, I will have a risk buffer, the red line, dotted red line there, which is not more than 80%. So don't use more than 80% of the resources. Now, with those intent in mind, and the system continuously looking at the data every 5 minutes, as soon as these recommendations of this new intent is sensed, the system starts giving you recommendation. And these recommendations are optimization recommendation, where you can optimize them manually, you can schedule certain optimization, or you can automate this process so that the system in an autonomous way can go ahead and make these changes to the environment to make sure that the workloads are optimally getting the performance they need. So what happens when you click on optimize? Once you click on optimize, I don't know whether the animation came through on Zoom or not, but essentially the proactive placement happens across these clusters to make sure that we are able to meet the operational and business intent. And again, as I said, you do not have to screen watch this and look at optimizations as they come and click on a button, but you can automate them completely so that we can continuously do the VM moves and the storage moves if needed across the different clusters to get the performance you need. Now, one performance problem happens because of constrained resources in a data center. The second happens because of sizing. Now, the system automatically also looks at the sizes of the VMs and continuously goes ahead and reflects if VMs are oversized or undersized, because of oversized VM or an undersized VM can both have performance problems, not only on them, but on others as well, especially in case of oversize. I don't want to go into ready time and wait time and so on and so forth, but you get the point. Now, if that's happening, the system again gives you those recommendations that you should be able to resize certain VMs or exclude certain VMs from this analysis completely. Now, that's where this particular right sizing is done, not only being aware of what is happening at the infrastructure, but also understanding what's happening in the application. Um, Now, there are two cool things over here I would call out. One is that understanding application behavior and memory utilization is not simple. To do that, you need an agent. But with vRealize operations, being a VMware product, gets the benefit of leveraging these metrics directly from using our patented VMware tools technology, which means we are able to bypass certain metrics through VMware tools right into vRealize operations, and which give us the context of what's happening inside the application without having you to deploy any agents or pass any credentials and so on and so forth. So that's where we do application aware right sizing. And the second is, as I said earlier, right sizing should not be done based on what the VM has used in the past, what the VM is using today, but it should be done based on what the VM would be using in the future. All right. And mostly in a regression mode or in a linear model, you will have things growing in the future. And as things grow in the future, you want to right size for that in the future. And that's where we do forecasted based right sizing to ensure that if you right size a workload today, you do not have to right size it every few days or upsize or downsize it every few days, but it can be done for a good period of time, foreseeable future, as I call it, to ensure that you do not have to make too many changes in your environment, because that can have poor impact on applications as well. Okay, now with right sizing and with proactiveness being covered, let's talk about recoverability as well, right? So this is where alerting comes into picture. You get alerts, you're able to take actions, and usually you do alerts on known issues, which means you know a problem, it triggered, and you want to go ahead and take an action. Let's talk about some of the intelligence in the artificial intelligence in the system, which takes care of alerting as well. So again, as I said, the system derives the topology, what you see over here. Sorry, it's a little small screenshot, but you see the related scope over here, which is a topology, which is defining how things are related to each other. Based on this topology, you're able to go ahead and derive how a given alert has a relational proximity to other alerts in your system, so that you can club these alerts together and point at a potential problem or an incident which is happening in your environment. So here I have an alert, which is virtual machine has CPU contention due to multi vCPU because it has a lot of co-stop, and again it's a hugely configured VM. Now that's the alert, and you can see that this particular alert, we've done some recurrence analysis, has happened 299 times in the last 30 days, which means that this is a chronic problem. So the system automatically goes ahead and does that analysis for every alert and tells you whether it's something which has happened just once or has it been happening for a number of times. Again, that's a question which you will usually ask when you're troubleshooting. But here we are trying to use AI to determine that and go ahead and provide that information automatically. At the same time, the other question which you ask when you're troubleshooting is it my problem or is it others are facing this as well? Especially when the alarm goes off, the fire alarm goes off in your apartment. And the first question you have is it my house or is everybody else's, right? You go ahead and look out. Now, I do that in California with California fires out there. But anyways, coming back to the topic, you want to make sure that is it my problem or everybody else's as well. And that's where we do a peer impact analysis to see if there are any active occurrences of this particular alert on all the peers. And the last one is topology graph analysis, which means that I want to make sure that whether this alert is localized to me and my peers because of a resource problem within myself, or whether it's coming from up and down the stack. Because guess what? I have a dependency available now, which means this VM might be having a CPU problem because the host has a problem. And you can see there's an alert on this host as well, or because the data store has a problem because IO wait is kind of creating a problem. So again, finding that root cause across the topology is what we're trying to do with the alert correlation. Now, the second piece uh, is how do you start with an alert, right? You have hundreds of alerts in the environment. How do you pick one and then start with that one? That's where the system automatically leverages AI to give importance level to alerts. So what you see in the center is the derived rank of a given alert. So you can have an alert which has a rank or importance score of very high, while another alert which has the importance score of very low or low. Now, this is done by two methods. And then the composite of both the methods is what is leveraged to derive the importance of a given alert. The first one is alert frequency analysis. Now, if a problem is happening too many times in your environment and you've not taken care of it, chances are it's not important to you. Now, that's one. The second is the spatial probability. So here, one is temporal probability, which is a part of the triggered alert data set. So how many alerts you have, how many times an alert has triggered, and what is the spatial probability, which means how many objects that alert is related to, and it might cause an impact to. If the causal relationship is huge and the alert triggerance is rare, it means that this particular alert is rare and hence it should be given rare and highly impactful, and hence it should be given more ranking or a higher ranking. So that's alert frequency analysis. The second one is user interest analysis. Now, this is important and this is critical because this is where a user or a set of users in a given system um, often leave their traces when they're looking at a data object. Now, again, we are not talking about tracing you in terms of where you're moving, like some companies do, but essentially this is more about what the user behavior is towards certain objects, right? So if your behavior towards the SQL Server VM or an application is very critical, it means hundreds of people are kind of looking at that object every day, day in, day out, through reports, through summary pages, through user interaction within the product, it means that that particular object would be given higher ranking as compared to the others. And that is access telemetry data set, which is used for deriving what exactly is the pattern of usage. And that derives the user interest analysis. We take a composite of both of these in order to come up with the importance level and derive what the importance score is for the given alert. Now, talking about enough of talking about the backend, let's just talk about how it appears in the front end in the product. So again, you can see As you look at all the alerts in vRealize operations, you can see how exactly the alerts have different importance score, which are fully autonomous and driven by the system in order to give you a starting point of prioritization of your problems so that you can work with. I hope I can get such a system which can prioritize all the feature requests I get from customers. Okay, that'll be a good product idea for a product manager as a customer. Okay, all right. So coming to the next topic over here is the user interest analysis. So again, you saw the alert and their uh, importance. Now that score also comprises of the objects and their importance. And within the product, you can access the relevance of the given object as well based on user interest analysis. So this is a good set of telemetry data which the system is brewing itself for us to leverage into a data set of alerting and giving and prioritizing problems. Okay, so I covered two topics. This is a good one. I have 18 minutes or approximately 18 minutes or maybe 13. But let's go through service reliability in the last piece of root cause analysis. I'll jump through this one because I do want to go to a demo, which is pretty interesting. Okay, so the troubleshooting process, and I think I spoke about this earlier as well, but essentially you start with something. You start with an alert, a phone call, an email, a ticket, a hallway conversation, and so on and so forth. And then if you are being called for a problem, you start investigation. And some of the key things which you ask is again, time, frequency, what changed, where is the problem? Has it ever happened in the past? Then you start reviewing what you have on hands. You go into your metrics, your events, your logs, your knowledge base articles, and you try to find out what's going on and try to find some kind of an evidence within those data sets. Again, those can run in this process can take around a week in certain cases or more, depending upon how big your environment is and how complex the problem is. But the reason you're reviewing this data is because you want to formulate a theory in your mind as to what's the root cause of this problem. What is the potential root cause of this problem? And you start collecting evidences, you start writing your root cause analysis document, and start hinting towards what could be a solution. And that's a typical troubleshooting process. And then you start looking at remediation steps. Again, these steps are not linear in any fashion because I know that in data centers and environments, they're all jumbled up depending upon what the criticality is. You might not want to do root cause analysis, but you want to go ahead and fix and remediate things first, and then look at the root cause analysis. But essentially, these are the steps which are done. And in my experience, it can take days, if not months, for chronic problems which happen in an environment, especially the ones which come and go and which are performance related and not so much configuration related. And they might be configuration related, causing performance problems, but they're so highly unrelated in human mind that it's hard to put those pieces together to find that root cause. So what we are trying to do is essentially solve that problem. How do I reduce this time span of going from start to stop, which will ultimately reduce the mean time to recover and mean time to innocence, as I call it, MTTI, to say, hey, it's a problem, this is a root cause, or this problem doesn't even lie in this particular space, it's somewhere else. Now that's mean time to innocence. But essentially, doing this entire process in a fully automated way is not easy. And hence, even if we can get to a potential root cause with certain degree of accuracy, just like forecasting, you are in good hands by any means of technology today. And again, this evolves and moves forward, and I will not talk about the future, but this is kind of the direction. So essentially, as a user who's investigating a problem, you if you have a workspace which has the scope which you're working on, the time which you're working on, and then across your environments for any kind of resources, whether it's network, storage, compute, or whether it's any kind of telemetry, whether it's metrics, events, logs, and so on and so forth. If you're able to bring all of these things together in a common workspace, and the system can automatically derive based on scope and time what your potential evidences are, then we will have a victory, is what we thought when we started this project. So let's look at how it manifests today. So talking about the AI in the backend, I'll not take a lot of time here. I do want to do that demo, but essentially you measure, you analyze, you learn, and you rank. And those are the four things which are involved in the entire process. You measure every given incoming data point, which can show certain degree of performance, availability, configuration, problems across the scope, or even capacity in certain cases. You get events, which could be violations, faults coming from the source, or just simple text messages. Again, you look at properties, which are a big source of configuration changes happening in the environment, and they not only help with configuration or performance issues, but also compliance, right? And then you look at logs, traces, and net flows. So right now the scope is metrics, events, and properties. And this is where the disclaimer comes in. We're moving into getting logs, traces, and net flows into the system as well. But with the first three events or first three set of resources, we analyze based on problem scope, problem time, and problem impact, which is also termed as the radius to which the problem is manifesting or is impacting. Um, and that's where you kind of start finding the neighborhoods in terms of where the problems are. And then to learn that behavior, there are change patterns in events, configurations, and in metrics. And all of them are learned in order to go ahead and get to probability or the p-value and the change magnitude within a given time proximity, and do a sentiment analysis to come up with what exactly are the evidences based on their frequency, based on criticality, based on the hypothesis, which is continuously testing them, and come up with what are the outcomes. And there are three different outcomes or three different set of evidences which come out, which I'll talk about in a second. Now, those evidences are the one which are being filtered down through millions of data points, which can be across a given scope, across different technology, across different stacks, and then presented to a user so that now you can minimize that whole process of days and weeks and months to troubleshoot into a few minutes or hours potentially. Let's look at that and how it is done, right? So this is done through something called the troubleshooting workbench within vRealize operations. It comprises of two inputs from the user, and sometimes those inputs are automatically derivated by looking at alerts, or they are derivated based on the user itself who might be exploring in the product. So on the left hand side, you have the dynamic full stack topology to define a problem scope. And on the right hand side, on the top, you have the dynamic time range to define a problem scope. Again, this is all about answering the two questions. What is the time range when a problem happened, and where approximately the problem happened? I mean, those are the two simplest things which you should know about a problem. And that's the only known you need to know about the unknown, right? Once you've given those two inputs, the system automatically drives, finds out events, property changes or configuration changes, and anomalous metric behaviors across that entire stack, which you see on the left hand side, and brings them and bubbles them up for a user to be able to go ahead and analyze and look at, right? And that's kind of the space of root cause analysis. And I'll give you an example of this as we move forward. And secondly, if you find an interesting behavior or a potential root cause, how can you confirm the final threads in terms of where that particular issue is brewing from? And that can be done through something called metric correlation. This is another form of AI which is based on pattern matching to be positive or negative pattern correlations or negative correlations. Sometimes we call them inverse correlations as well, in order to find the root cause of a given problem. And that's where metric correlation comes into picture. Now, the idea is that if you have a database, let's say SQL, and not saying that SQL is bad, but essentially in case you are losing transactions and transactions per second is getting dropped drastically, then there is there is a pattern or a linear pattern in that particular behavior, which means transactions are going down. And once that is happening, you can have a problem at the database layer in the SQL queries. You can have a problem in the application layer because they're not calling the right set of queries, or it's not load balanced across a load balancer and so on and so forth. You can have a problem in the infrastructure, which starts from a problem in the VM, a problem in the, guest OS, virtual machine, ESXi host, data store, disks, virtual array, or if you're using vSAN, or if you're using some other storage array. It could be anywhere in the system. And how can you quickly look at one metric and say, across this entire scope, which you see on the left-hand side, go and correlate this metric and find any positive and negative correlations which are like this particular metric. And that's what the system automatically does for you, and finds out that in this example, you can see that I have a pattern of memory reserve capacity shooting up for a given host. And at the same time, there's a correlated metric of capacity remaining on the storage jumping down, and that is completely correlated. Now, there could be many such examples which the system can derive automatically. Um, all right, so let's do a demo. I think we're right on time. I will just go ahead and stop sharing and share once again with my demo system. I do see a question. 5 minutes left. Okay. Okay, so let me just go ahead and oh, I have 11 here. Go back a slide. Okay, so here I'm demonstrating an application, which is again, which is run by a company called Shutter Entertainment. A quick background, because I have less time, is that this application, or this Shutter Entertainment, is rolling out a survey which will go out to find out what their customers would want to watch as the holiday season movies during this winter break. And they go ahead and roll out. They want to go roll out this application across the country, and they're leveraging the Shutter CRM app. The CRM app is running in their Wisconsin data center, which is powered by the VMware SDDC stack. They plan to roll out the survey using the CRM survey module. So this application is a custom built application, has a survey module built in, and they want to do a rollout of the survey uh, across the United States. They've already done this in the staging and scale environment. Everything works fine. Then they're ready to go ahead and go live with the subscribers. So let's look at this particular scenario as to what happens on the go live date. So as a user, I receive the survey from Shutter, and I just trying to go ahead and click to start the survey. And essentially, this is what a business problem looks like in a lot of senses when there are incidents which happen in the backend. And how do you find that root cause? So here, the survey application is down. I'm not able to reach the survey application. So as a user, of course, I'm dissatisfied and I want to watch my movies. I go ahead and reply to the folks in Shutter and say, hey, Shutter support, your survey is not working. Regards, Sunny, and just go ahead and send it out. All right. Okay. So now the Shutter team will receive my response, and of course they will start. That's the source of the problem, right? That's where the problem starts. So again, let's switch over to vRealize operations and see how we can tackle this problem. So I go ahead and search for Shutter CRM. Let me see, CRM app. So there is my app right there. Click on it. And vRealize operations has automatically detected this particular app, either through network flow data or through tags, which you can create this application in the system, or through service discovery. And yes, off the bat, I can see that there's a problem in the application. The Shutter CRM app has a problem. And even so, the Shutter app tier has a problem. I can see some alerts as well. Oops, sorry for that. Let me just go back. As you can see, sometimes the recorded demo plays up. Okay, so you can see that I have the CRM app, I have the app tier, which has an alert, and also the CRM VM. At the same time, you can see I have some alerts on the right-hand side, and I can see that off the bat, the Shutter CRM survey VMs has disk IO read and write latency. Now, that could be a problem. That tells me that the VM is struggling, but I don't know what the root cause is. The application health itself is degraded. So let's just click on this troubleshoot button right here, which launches me directly into the troubleshooting workbench. Now, what you see over here is on the left-hand side, the topology of the CRM app. So I can see all the VMs which make up the app, all the tiers, and also I can see all the infrastructure which make up the app. And right off the bat, I can see that at around 11:18 p.m., when the survey was rolled out, or at around that time, or after the survey was rolled out, there is a config change which has happened in this particular CRM survey VM. It has moved from a vSAN data store to a local data store. That's not good. At around the same time, I can also see some other behavior, which is on this particular CRM survey VM itself. And I can see the outstanding IO requests is starting to climb up. And looks like 11:18. So let's just look at that. And I will just go ahead and pin these evidences. So I've pinned the previous one, I've pinned this one as well because they all look interesting to me. And then the last one is I will pin this one as well because I can see the disk latency has started to shoot up, and this was one of the alerts, and it's gone to 5K, which is extremely high, right? That at that time things will just stop working. Now can now see that these are the evidences, and since I've pinned them, I can go into the metrics tab and start looking at what exactly, or start comparing them just to be sure that that's my root cause. Now I can see that all these are behaviors are manifesting at the same time. So let me just go ahead and combine them to see if I can stack these charts together. And now you can see that all these stars are aligning. And this is an important piece, right? Where you can see a change happening. And as the change happens, I can see a high jump in the OIOs, or outstanding IOs, and latency. Now, within seconds, or I would say minutes, we've been able to potentially find the root cause. There was a change done in the environment because of which the survey application stopped working. And it was a movement from a vSAN data store, which was essentially a powerful data store where I was running my application, to a local data store. And that's the change which has caused the issue. Again, I can go into the details of who changed that within log insight and catch the person as well. But essentially, let's look at the potential evidence first and click on this VM and try to solve this problem first. So here is where you want to recover out of this situation, right? You have high disk latency. I have various suggested actions over here, but I know that I can move the virtual machines, disks from here, or let me just directly go into actions and take an action of, because I know what exactly is the problem, I'll move that particular VM from the data store, from the local data store to the vSAN data store. So here's the one which is running on the local data store, and I want to move it to the vSAN data store. So let me expand that and show it to you. There you go. That's the destination data store. And click on begin action. So this is where the system uses that action framework, which can be fully automated as well if you wish to go ahead and move that VM. So let me just go ahead and look into this particular task and see what's happening. So you can see the move VM is completed at around 11:36 p.m. So 11:18, the problem happened. By 11:36, I was able to take a remediation action as well. And you can also see that this particular move is completed, and the system kind of confirms that the actions of moving the CRM server from local to vSAN is completed. And let's just go ahead and the script, okay, it's completed. And let's just go ahead and search for that application again. So Shutter CRM app, and click on it. All right, voila. So I can see that things are green now. The health has started to come up, and the problems have started to go down. Anomalies have started to go down. Things are green, and my application is up and running, which is always a great sign. And now, as a user, let me just go ahead and open that survey. And beautiful, the survey opens up and it's asking for my questions. And that's what you want to see when you send a survey to your user, and not 404 not found. Okay, with that, let me just go ahead and quickly conclude. So essentially, we looked at how we can leverage AI for proactive operations how we can look at AI for dealing with events and prioritizing them for ourselves, and so that we can target the right problem. And lastly, how we can leverage AI to find root cause across a given scope or full stack and a time frame, which can automatically go ahead and filter out evidences which are important to look at and derive an action-based remediation as well to make sure that the service is not only recovered but also reliable going forward. I don't see any questions at this moment. I see a lot of attendees. So if you have any questions, feel free to ask them. Otherwise, that was the end of my presentation. Thank you once again. And you were watching leveraging artificial intelligence to derive full root cause analysis or full stack root cause analysis. And yeah, if you have any questions, feel free to reach out on Twitter or come directly on my website, and I'll be more than happy to answer questions. With that, thank you so much, and you have a fantastic day and a great conference, Uptime 2020. Thank you, Runecast.